Hello, everyone, and welcome to FusionEPtalks, a student-led webinar platform for sharing knowledge about nuclear fusion, science, and engineering. I'm Dhaval, and I would like to introduce our speaker today, Dr. Satoshi Togo. Satoshi earned his PhD at the University of Tokyo in 2016 and then worked as a postdoc researcher at the Plasma Research Center in the University of Tsukuba in Japan. Until then, he focused on improving the SOL-divertor plasma fluid modeling. In 2018, he was awarded the ITER-Monaco Fellowship and focused on investigating the plasma at turbulence for 2 years. Since December 2020, he has been working as an assistant professor at the Plasma Research Center at the University of Tsukuba in Japan. Without further ado, I would like to give the stage to our speaker today. Thank you very much, everyone, and enjoy the talk.
Okay, thank you very much for introducing me. Thank you so much for introducing me. And also thank you for coming to this webinar during your busy time. My name is Satoshi Togo, and I belong to Plasma Research Center in University of Tsukuba in Japan. And today I'd like to give a talk titled SOL-divertor plasma fluid simulations based on the anisotropic ion pressure with a virtual divertor model. So first of all, I'll give this seminar on behalf of the co-authors of my works shown here. So I'd also like to thank all of them first. So this is the outline of this talk. First, let me introduce some backgrounds of my work. After that, a plasma fluid model named AIP model, which we have been developing, is briefly reviewed. Then some numerical results are shown. And this talk will be summarized at the end of it. So first, let's begin with some introduction. As many of you may already know, most tokamak devices adopt the divertor configuration. And it is true for the JA demo reactor, which has been designed in Japan. The right figure shows an example of equilibrium of JA demo. The separatrix magnetic surface is created in a divertor configuration, and it makes the core plasma away from the wall. Then hot particles from the core plasma flow along the scrape-off layer and the divertor region, and finally concentrate on the divertor plates. The heat load on the divertor plates will be by one order higher than the tolerable level from the divertor material point of view without any mitigation. Therefore, handling of this huge heat load is one of the most crucial issues in demo. Here, I'd like to show how it will be severe to handle the divertor heat load in demo. The divertor heat load is usually evaluated by using 2- or 3-dimensional simulation codes. In the JA demo case, for example, a 2D simulation code, SONIC, is applied to quantitatively evaluate the divertor heat load. This table shows a rough estimation of the power balance in ITER and JA demo. JA demo is slightly bigger than ITER, but the fusion power will be 3-fold. This P-sep denotes the power across the separatrix, and it also will be 2 to 3-fold. Meanwhile, the tolerable heat flux on the diverter plates in JA demo will be about 10 megawatts per square meter, which will be similar to or a bit severer than that in ITER. Then we simply assume that the plasma wetted area is proportional to the major radius, and the diverter tolerable power P-div is estimated as shown here. So the gap between P-sep and P-div is the power we need to mitigate in the SOL-divertor region. The power mitigation is planned to be performed mainly by impurity radiation, so it is denoted by Prad. The fraction of it to Psep is estimated to be about 70% in JA demo, while it is about 50% in ITER. In order to keep a high radiation fraction, it is a usual way to keep the core density high because the radiation power depends on the electron density. However, it is predicted that the Greenwald density limit will be lower in demo than ITER. So it might not always be easy to keep a high radiation fraction. Therefore, it is said that handling of the demo divertor heat load requires a highly accurate control, and for that, highly accurate simulation models are required. Other than Sonic code, there are many SOL-divertor codes for divertor design, such as SOLPUS, UH, EMC3 Irene, SOL-H, and so on. Although there are some differences in some element models within these codes, the basic structure is similar. They have mainly three modules in charge of transport of fuel plasmas, neutral particles, and impurity particles. They are iteratively solved until a self-consistent solution is obtained. All of these modules are based on some physics models which are already understood to be essential. However, there are still some missing physics phenomena that might be important but not yet considered enough. We have been focused on some of the missing physics related to the plasma module. From the computational time point of view, the plasma module normally solves a fluid model, which is not based on the first principle. And we have mainly focused on the physics related to the pressure anisotropy and the sheath boundary condition. Here, let me briefly explain the anisotropy of the pressure or the temperature. First, we introduce V-para and V-perp, which denote the parallel and perpendicular velocity to the magnetic field line in the gyro motion of a particle. Then the parallel and perpendicular pressures are defined by the variance of the V-para and V-perp respectively. By introducing the velocity distribution function F, P-para and P-perp are defined by these formulae. And please note that SOL plasma pressure can be anisotropic due to the difference in the energy transport characteristics. And the anisotropy is relaxed by Coulomb collisions. And this figure shows a kinetic simulation result, which shows the dependence of the temperature anisotropy T-para over T-perp of ions and electrons on the plasma collisionality. The plasma collisionality is often quantified by the mean free path of Coulomb collisions normalized by the parallel system length. Here, the collisionality at the SOL upstream in demo is estimated to be 0.2 to 0.8, which means marginal collisionality. And the range of this collisionality is hatched in this figure. You can see that the ion temperature anisotropy is remarkable and is 0.2 to 0.3, while that of electron is small. Here, let me briefly explain how the anisotropic ion pressure affects the fluid simulation results. This equation shows the very basic form of parallel momentum transport of ion. Here, S and V represent the parallel 2B coordinate and the parallel ion flow velocity, respectively. The first and second terms in the parenthesis are called dynamic and static pressures, respectively. And please note that the static pressure is represented by the parallel component only. This equation means that the balance between the dynamic and static pressures determines the parallel ion flow V. On the other hand, in the conventional plasma fluid model, which is known as the Braginskii's equations, the corresponding equation is this one. In this model, the pressure anisotropy is not explicitly considered. And please note that the static pressure is represented by the effective isotropic pressure P, which is defined by this equation in terms of P para and P perp. But obviously, this P is different from P para, and the difference between them denoted by P delta P can be expressed like this equation in terms of P para and P perp. And in this conventional model, this delta P is approximated by this term under the assumption that delta P itself is much smaller than P. This is why there appears a new term called the parallel viscosity. However, please remember that the ion pressure anisotropy is not always small enough when the collisionality becomes marginal. So this delta P can be the same order to P. In such a case, the validity of this approximation is degraded, and thus the accuracy of the ion flow profile is also degraded. In addition, because this kind of fluid model solves a set of system equations, other variables like the density and temperature are also affected. Therefore, our basic idea to improve the accuracy is to simply go back to this very basic equation by introducing the anisotropic ion pressures. The other element that we focus on is the treatment of the sheath boundary conditions. Here we show images of the one-dimensional potential profile and the density profile in the vicinity of the divertor plate set at the right edge. As you may already know, a sheath region is created in front of the divertor plate where the ion density is larger than electron density. Because particles here are far from thermal equilibrium, plasma fluid models do not deal with this sheath region. Instead, they only deal with the quasi-neutral plasma region by imposing the sheath edge boundary condition derived from the sheath theory. One of the sheath boundary conditions is known as the Bohm criterion. This is a necessary condition at the sheath edge to obtain a monotonically decreasing potential profile in the sheath region. This criterion is reduced to one about the ion flow, that it is equal to or larger than the local sound speed, which means the Mach number is equal to or larger than 1. In conventional models, the sheath edge Mach number is fixed to be 1 or linearly extrapolated if it tends to be larger than 1. But this treatment is not a self-consistent one. On the other hand, in some conditions of experiments and kinetic simulations, supersonic ion flows can be generated. Then how can we deal with supersonic ion flows self-consistently? For this issue too, introduction of the anisotropic ion pressures works very well. With a parallel viscosity term, this equation is classified as a parabolic partial differential equation. Such an equation requires downstream boundary condition to be solved. This is why an explicit boundary condition of downstream ion flow is imposed based on the Bohm criterion. On the other hand, without the parallel viscosity term, this equation is classified as a hyperbolic parallel differential equation. Partial differential equation, sorry, because such an equation has so-called one-way nature. The ion flow V can be solved from upstream to downstream. Therefore, by introducing the anisotropic ion pressures, an explicit boundary condition of downstream V is no longer necessary, and supersonic ion flows can also be simulated self-consistently. And I'm sorry for this lengthy introduction, and this is the final slide of this part. It is efficient to investigate the impact of the anisotropic ion pressure on SOL-divertor plasma fluid simulations by a 1D model rather than sophisticated 2D or 3D models. But we have been developing a 1D plasma fluid model based on AIP called AIP model, which only considers parallel 2B transport. In this study, we approximate a SOL-divertor region colored yellow by a homogeneous magnetic field system like this. And then we apply our AIP model to this system and show some basic results. Then let me briefly review our AIP model. First, we explain the basic equations of AIP model. And then a virtual divertor model is explained, which is incorporated within AIP model to simulate effects of the sheath region. Here we show the basic equations solved in AIP model. All of them only consider the parallel transport. And 5 variables, that is density, parallel ion flow, parallel ion pressure, perpendicular ion pressure, and the electron pressure are solved by solving these 5 equations. The equations of particle continuity and electron energy transport are almost the same as those in the conventional fluid model. And please note that the equation of parallel momentum transport doesn't have the parallel viscosity term, and thus it is a hyperbolic one. And the equation of ion energy transport is divided into 2 components. One is for parallel and the other one is for perpendicular component. And collisional relaxation of the ion pressure anisotropy is expressed by these terms surrounded by dashed lines. And the relaxation time is given by this equation in terms of the ion Coulomb collision time. Finally, the plasma particle and heat sources are given to the right-hand side terms denoted by capital S and Q. Instead of using an explicit boundary condition on the downstream ion flow, AIP model adopts a virtual divertor model in order to simulate effects of the sheath region. In the conventional code, the edge of the numerical grid lies on the sheath edge, and there the sheath boundary conditions are imposed. In AIP model, on the other hand, a virtual region is set beyond the sheath edge, and artificial sink terms are put there so that the sheath boundary conditions are satisfied. The artificial sink terms for the 5 equations are shown here. Here, tau Vd and the coefficients G are input parameters to control the boundary conditions. And here we have some additional notes on the numerical condition. The realistic plasma exists in this yellow region, and the particle and heat sources represented by these red arrows are given in the SOL region. Beyond the sheath edge, a virtual divertor region is set. On the right side, we show a schematic image of the plasma profiles. In the virtual divertor region, the plasma is strongly damped due to the artificial sink terms. In this figure, it looks like we have one virtual divertor region for one sheath edge, but in the AIP model, two virtual divertor regions are rolled into one, like this, so that the periodic boundary condition can be applied. Then let's move on to the results. First, we show some typical plasma profiles. Here we give two sets of particle and energy sources in the SOL region to control the collisionality. It looks small changes in sources, but the collisionality changes by 2 orders. In this figure, we show parallel profiles of the density, Mach number, parallel ion temperature, perpendicular ion temperature, and electron temperature. The vertical orange lines represent the sheath edge, and between them a virtual divertor region lies. Then the red and blue curves represent the collisional and collisionless cases respectively. And please note that in the collisionless case, the parallel and perpendicular ion temperature profiles in the plasma region are qualitatively different, which reflects the effect of the introduction of the anisotropic ion pressure in the fluid model. In the collisional model, you can see that the difference between the parallel and the perpendicular ion temperatures, temperature profiles become smaller, which indicates the collisional relaxation. The ion temperature anisotropy in the divertor region becomes like this, and actually it is relaxed in the collisional case. Also, please note that the Mach number at the sheath edge is greater than 1 in both cases, which means the Bohm criterion is automatically satisfied. And the trend of the ion temperature anisotropy is investigated in detail, and we obtain this result by AIP model. On the left side, we show again the kinetic simulation result. So the trend of collisional relaxation of the ion temperature anisotropy in the kinetic simulation is qualitatively and semi-quantitatively reproduced by AIP model. In the kinetic simulation, it is also reported that supersonic ion flows are generated when electron cooling is introduced in the divertor region. Here, M plate and M throat represent the Mach number at the sheath edge and the X point, respectively. The parameter C represents the magnitude of electron cooling in the divertor region. And it shows that the Mach number at the sheath edge becomes larger than 1, while that at the X point stays at 1 when electron cooling is introduced. And similar simulations are performed in AIP model, and the result is shown on the right side. You can see that the trend is reproduced by AIP model, although an effect of finite grid size appears. Finally, let me summarize this talk. The ion pressure or temperature might be remarkably anisotropic at upstream SOL in demo due to marginal collisionality. And in SOL-divertor cores, a plasma fluid model has been applied to plasmas in which the ion pressure anisotropy is approximated by a parallel viscosity term. And we have been developing a 1D plasma fluid model based on the anisotropic ion pressure called AIP model. In this study, we first apply it to a homogeneous magnetic field system to investigate the impact of the AIP on plasma profiles. A virtual divertor model is incorporated within AIP model in order to simulate effects of the sheath region and let plasma satisfy the sheath edge boundary conditions. And following things are shown in the homogeneous system simulations. The Bohm criterion is automatically satisfied. The trend of collisional relaxation of the ion temperature anisotropy in the kinetic simulation is semi-quantitatively reproduced. And the trend of supersonic ion flows due to electron cooling in the kinetic simulation is reproduced. And that's all. Thank you very much for your kind attentions.
Thank you very much, Dr. Togo. It was a really insightful talk. I will now open the talk for a question and answer session. So we have the first question from Jan Boshoff. I will, yeah, you can go ahead and ask the question. Yeah.
Hi, thank you so much for the talk. What wasn't clear on the graphs is exactly the length scale that you were using, because it looked like was labeled with meters, and that seems really large, especially if we're talking about the size of sheaths.
Which one do you mean? This one?
Yes, on the x-axis, the S is that physical length in meters.
Yes. So, but in between these orange lines, we have a virtual divertor region, and here we have how can I call it? It is a kind of how can I call it? Simulated sheath. So this is not a true sheath.
Yes. Okay.
Yeah. So so it's bigger than the realistic sheath. But we hope by using this model, the effect of sheath can be reflected to the plasma region. So this kind of unrealistic sheath is still enough to reproduce the sheath boundary condition.
Okay. Yeah, thank you. And is that the length scale to do with any of the physical plasma properties, like the can you show it in terms of maybe the dBi length or the Larmor radius?
Yeah, maybe it's possible, but we usually normalize this length by the connection length between these two divertor plate. No, these two divertor plates.
Okay.
Okay.
Thank you.
Thank you for the question.
All right, then seems like there are no more questions. So I'd like to thank our speaker for today, Dr. Satoshi Togo, for the talk, and also our audience for joining in. We will see you. Have a nice day wherever you are. Thank you very much.
Thank you very much.